Hi, welcome to part 2 of chapter 1. This will cover sections 1.5 to 1.7. So this main part will discuss measurements, numbers, units, precision, and accuracy. So there are numbers in chemistry. There is math in chemistry. And numbers, they do play a major role. Many topics are quantitative, so they have a numerical value. Some of the things we're going to talk about are your units of measurement, the quantities of measurements and how they're calculated, uncertainties in your measurements, our favorite significant figures, and one of the most powerful tools you will learn is dimensional analysis. So your units in chemistry and most of your science classes, you will be using the metric system or SI units, okay? SI stands for International System of Units. It's French. So depending on what you're measuring, it has a different unit and a base unit. So for example, length base unit is a meter. So you could have a meter, you could have a millimeter, you could have a centimeter, you could have a kilometer. What do they all have in common? The meter. So these letters here are the prefixes. And those prefixes have a numerical value, okay? But in this slide here, I just want you to know that these units right here are your SI units that we will be using throughout the year. And the prefixes that I mentioned previously are listed here. So these are your prefixes. So the abbreviation. Okay, so on the last slide, I used the K, which means 10 to the 3. So 1 kilometer is equal to 1,000 meters, or 10 to the 3rd meters. So the K means 10 to the 3. You might want to keep this table handy. It's also in your book because we are going to be converting from units, and you do have to know what the prefixes mean. And when you do your sample exercises for your summer assignment, there are some conversions using some of these units. So refer back to this. Volume does not really have a base unit per se because it is a derived unit. When we measure the volume of a substance, you measure the 3 dimensions here. So you have meters times meters times meters. So you get meter cubed, and that is your volume is always a length cubed. And depending on what you're measuring your length in, that's what's cubed. Okay, but what we most commonly refer to volume is the liter or the milliliter. Okay. And here milli, the little m, means 10 to the minus 3. Here are some pictures of glassware. You're going to have to remember the names of glassware from last year, and there will be some new pieces of glassware we will use this year that we didn't use last year. So the first one's a graduated cylinder, then you have a syringe and a burette. We didn't get to use the burette because we weren't in school for acids and bases, but when we do titrations later on in the year, we will use burettes a lot. So these all deliver various volumes, okay? If you want to have one specific volume, then you would use a pipette or a volumetric flask. Normally on your volumetric flask, there is a line, there's just one line, and say this was 1 liter. That means if you fill it right to that line, you have 1 liter. So these are only good for one specific volume. These you could use to measure multiple volumes. Temperature. In science, we use Celsius and Kelvin mostly, but in everyday life, you will see something called Fahrenheit. That is the English unit for temperature. So temperature is normally considered the hotness or coldness of an object, and it's determined by the flow of heat. So heat likes to flow from high temperatures to low temperatures. So if you touch something and it feels hot, that means the item that you're touching is at a higher temperature than your hand. If you touch something and it feels cold, that means that your hand is at a higher temperature than the substance you're touching. So the heat is traveling away from your hand, giving you the sense of a cold feeling. Remember, there's no such thing as cold. It's just the removal of heat. So the SI unit for temperature is Kelvin. And in order to get Kelvin, if you have Celsius, you're going to add 273.15 to get Kelvin. The nice thing about Kelvin is they developed this temperature scale, so there are no negative temperatures in this. The lowest temperature on the Kelvin scale is 0. And this 0 is called absolute 0. At absolute 0, your kinetic energy is 0 and there is no motion. So they define the lowest temperature as the temperature where items stopped moving. And they made it absolute and they called it 0. So Kelvin starts at 0 and goes up. Now for Celsius and Fahrenheit, you can have negative temperatures. In Celsius, which is the middle scale here, you have water freezes at 0. And it boils at 100. In Fahrenheit, it freezes at 32 and boils at 212. Okay, and here are your equations to convert. So if you wanted your temperature in Fahrenheit and you had it in Celsius, you just plug in your Celsius temperature here. You do 9 divided by 5 times that plus 32. If you had Fahrenheit, you would subtract 32 from it and then multiply it by 5 divided by 9. You will need these equations to do your summer assignment, so make sure you have them jotted down. So there's two types of numbers that you're going to encounter in science. One is called what we call an exact number. In exact numbers, there is no error. There is no error in these types of numbers because it's an exact thing. It's like when you count something, you know exactly how many you have. So in 1 dozen, you have exactly 12 eggs. There's no error in that. It's not really like you're measuring it or there's any uncertainty. There's no error or uncertainty. Inexact numbers are ones that you measure. Whenever you measure a number, there is some uncertainty to your measurement. And it depends on how you measured it or determined the number. If you're using some piece of equipment, that equipment has limitations. Okay, and the limitations of that will result in equipment error. Then depending on how you measure, the way you look at it, the way you read the scale, that will have some what we term human error. So let's discuss the uncertainty in measurements a little bit more. So in this case, different measuring devices have different uses and different degrees of accuracy. So depending on your equipment, you will be able to measure to better precision or worse precision, depending on what you're using. No matter what, all measurements have some degree of inaccuracy. Okay, the last digit measured is considered reliable but not exact. So what does that mean? So here we have a thermometer, and you can see here, marked on our thermometer is 25 and 30. And our liquid is right here, somewhere in the middle. So we know it's at least 25, but we know it's less than 30. So we're kind of guessing where it is between 25 and 30. So we know the 2 for sure, and the 7 is our guess. This is our guess. So this is our uncertain or our estimate. And it depends on how good your piece of equipment is. So if you look at this diagram here, this diagram has one marking, 0 and 1. Now looking at this, I could say, oh, roughly here is half. So it's a little bit more than a half. So I'm going to guess that it's 0.6. Was this 0.6 written anywhere on my ruler? No, it was an estimate or a guess. So this is our uncertain measurement. And you are allowed to guess the last digit. Now we went and we got a slightly better ruler, and it has more divisions. So now I can see that, yes, in fact, it is 0.6, but it's not exactly on the 0.6 line. It's a little bit off of it. So I'm going to guess the 1. So in this case, the 1 is uncertain. And we are allowed to guess that because we know for sure that the 6. So you're allowed to have one uncertain decimal place or digit. Now down here is an even better ruler. And if we zoom in, we can see that yes, it is greater than 0.6, but it is less than 0.61. So it's somewhere in the middle. So here we can guess the 7. Now, if you look at this division here was the 1's place. And we guessed to the 10th place. This division here was the 10th, right? So we could guess one more decimal place. And this division here was the 100ths. So we could guess one more. So you're always allowed to guess one more place than your equipment is marked. So look at the markings on your equipment and realize that you could always measure one place that is not marked. So how do you make a measurement using a graduated cylinder? We will be using graduated cylinders quite often in class, so it is important that you know how to actually measure things. So the first thing is you have your liquid in your graduated cylinder and you look at the scale that starts with the low number and then goes to the high number. And in the box, we're zooming in, and we want to know what each of these lines represent. So if this is 20, what is this line right here, and what is this line right here? Well, as it turns out, each line is 1 milliliter. Okay, and you could look at that by, like, look down here. We have 10, and then we have 15, and there are 5 divisions in between. So each line is 1 milliliter. Now, when you are looking at your graduated cylinder, it is important that your line of sight is lined up correctly. So you might have to raise the graduated cylinder to the top of the lab bench so that you can have your eyes looking right at where the liquid is. So you want your eyes to be right on line with the meniscus. The meniscus here is this U shape. The bottom of the meniscus is where we want to measure it. But it's important that your eye level is on target with the bottom of the meniscus, because if you are below it or above it, you will get an incorrect reading. So here we are looking at it, it's in between 21 and 22. So we know for certainty it's at least 21 milliliters, and we're going to guess, and I don't know, that looks about maybe a little bit more than halfway. So this was a guess. You might have said 0.5, and that is fine too. So here's an example of where the measurer was not lined up properly. When they are lined up properly, they get 19.70. Now, notice this has 2 decimal places where our previous one only had 1. But look at our divisions. It's going from 18 to 19, right? So each line is 0.1. So if each division is to the 10th place, we can always guess one more place. Now, what if I was looking down at it? I would actually get a lower reading. If I was looking up, I would get a higher reading. So it is important that you, when you're measuring with a graduated cylinder, your eye is on level with the bottom of the meniscus, and that you record it to the proper number of decimal places. Remember, you look at the measurement and you look at the smallest division. So in this case, 1 milliliter was the smallest division, so you could guess one place beyond that. In this one, the divisions was 0.1 milliliter, so you could guess one decimal place beyond that. So let's look at this diagram right here. Here we have three pieces of equipment to measure volume. We have a beaker, a graduated cylinder, and a burette. And if you look at each of these, the beaker has the least amount of divisions. Then the graduated cylinder is better, it has more divisions, and then the burette is even better, it has even more divisions. So which one of these equipment is the most precise? Well, it turns out the burette. Because look at the measurement value. Here, I know my level is in between 20 and 30. So the 2 I know for sure, this I know for sure. The 8 was a guess. In my graduated cylinder, I could see that the water level is actually in between 28 and 29. So I know for sure the 28, and I'm just guessing how much above the 28 it is. Okay, so notice the division on the beaker was 10 milliliters. So the burette now, if you look here, going from 28 to 29, and there are 10 lines in between. So my division here is 0.1. It's my division. So when I do that, I see that it is 28.1, 2, 3, but it is not exactly on the 3. So I am guessing the 1, because I think it's a little bit above the 3. You might argue and say it's right on the 3. Okay, but notice this number is 28, is 28.3, and this is 28.31. So the more divisions you have in your equipment, the more decimal places you could get, the more precise your measurement. The lower your error or uncertainty. So let's try to measure these. So here I have a graduated cylinder. I see I'm going from 40 to 50, so that is 10 milliliters, and there are 10 lines in between. So each line, or each division, is 1 milliliter. So let's zoom in. Again, I want to measure the bottom of the meniscus. So this is 40, 41, 42, 43, and I feel it is right on the line. So why did I put 0.0? Because I have to guess, and I am guessing it is right on the line. If my division is in the ones place, I can guess one more place after that. Here I have a burette, and I see that if I went from 20 to 21, there are 10 lines, so each line or each division is 0.1 milliliters. Terms that we throw around a lot, and sometimes we use them like they mean the same thing, but they really don't, are accuracy and precision. Precision is how close multiple measurements are to each other. Precision is how repeatable your measurement is. Accuracy is how close you come to a known value. So it's how close you come to the accepted value. So in every textbook I've ever seen, there's always the dartboards. This one's always easy. This one, you're nowhere near the target and your darts are nowhere near each other. So you have poor accuracy and precision. So both are bad. And over here, both are good. Every dart is in the center. So it's repeatable and it's hitting the center, so it's very accurate. Here, all the darts are in the same place. So they have good precision, but they are nowhere near the target, so poor accuracy. Remember, the center here is your accepted value. This one here, the arrows are nowhere near each other, so that's poor precision, but they are all the same distance away from the center, so that's good accuracy. And it's important here to note that standard deviation will estimate your precision, and percent error estimates your accuracy. Significant figures. Significant figures are needed so that we know how good our equipment is. The more places or decimal places our equipment has, the more precise it is and the more significant figures it has. So if I give you a measurement, how do you determine which numbers are significant and which numbers are just placeholders for the decimal point? Well, all non-zero digits are significant. So if you have a number that is not zero, it is significant and it counts. Zeros that are sandwiched between non-zero numbers are significant. So let's take this measurement here. This has 2 sig figs. Zeros at the beginning of a number are never significant. So these zeros here don't count. They are not significant. Zeros at the end of a number are only significant if you have a decimal place. This number here has 1 sig fig. This number here has 3 sig figs. When numbers are written in scientific notation, all the digits that are written here are significant. So, a nice little rule of thumb is if your number is less than 1, you draw an arrow to the right until you reach a non-zero number. All the digits you did not cross out are significant. If your number is greater than 1 and there is no visible decimal place or decimal point, you draw your arrow to the left until you reach a non-zero number. All the digits you did not cross out are significant. So this is 1, this is 2, 3. If your number is greater than 1 and you see a decimal point, all digits are significant. Sometimes you might see a bar written over a 0. So in this case, that means this number is significant and all the ones to the left. So that this has 3 sig figs. So let's try to write how many sig figs each of these measurements have. So this number is less than 1. So I draw my arrow until I reach a non-zero number. So this has 3 sig figs. Less than 1, 3 sig figs. Greater than 1, and I see the decimal, so all digits count. Greater than 1, and I see a decimal, all digits count. Less than 1, greater than 1, but I don't see the decimal point. So I draw my arrow until I reach a non-zero number. Now that we're experts at figuring out significant figures, let's do some math with them. What happens when you add and subtract? When you're adding and subtracting, you must round your answer to the least number of decimal places. So if you look at my example here, this has 1 decimal place, this has 2, so I must round to 1 decimal place. Now I purposely put the second example because neither of them have decimal places. So when there are no decimal places, you must round to the regular place, not the decimal place. So this here is my last significant. It's the tens place, and this is the ones place. So I have to round to the tens place. So when I do 10 minus 4, I get 6, but I have to round that to the tens place, which rounds up to 10. Because this piece of equipment has the least amount of precision, because that's telling me the divisions are very large. So let's do this one here. I have 0.950, so I have 3 decimal places, and this one has 4. So how many decimal places should my answer have? When you add them together, your answer should have 3, and make sure you put a unit. Multiplying and dividing, we round to the least number of sig figs. So for this example, this has 2 sig figs and this has 3, so my answer has to have 2 sig figs. Here, this has 3 sig figs and this has 2, so my answer must be rounded to 2 sig figs. Now let's try this one. So 55 times 22.1. If I just punch that in the calculator, I'm going to get 1,215.5 centimeters squared. Now I need to round it to significant figures. This has 2 significant figures. This has 3. So I need to have 2. So you start at the left and you count in 2 places, so I must round to the hundredths place. What happens when they're both combined? So we're going to have to do our order of operations. So we're going to subtract on top first. So when you subtract, you must have the least amount of decimal places. So our number would be 2.0 grams. So now I have 2.0 grams divided by 2.00 milliliters, which gives me 1, but how many decimal places do I need? So this has 2 sig figs, this has 3, so my answer must have 2. The last topic we're going to cover is dimensional analysis. This is basically you use the units to help you. So if you need to convert from one unit to another, you need to know how they are related to each other and then use the units to help. So in this example here, I'm saying 1 inch is 2.54 centimeters. So that is our conversion factor. Conversion factor is when one unit is equal to the other. So you must use that to convert from one to the other. So here I am given 1.000 yards, and I would like to know centimeters. So I don't know how many centimeters are in a yard, but I do know in 1 yard there are 3 feet. So the unit I want to get rid of has to go on the bottom. And So that's important. So in 1 yard, there are 3 feet. I'm getting ahead of myself. So if I stopped here, my yards would cancel out and I would have feet, but I don't want feet. So I want to get rid of feet, so I put feet on the bottom. And I happen to know in 1 foot, there are 12, let's do a different color. 12 inches. So what happens to my feet now? Because they are on top and on bottom, they cancel out. So I would have inches, but I don't want inches. So I would like to get rid of inches. In 1 inch, I have 2.54 centimeters. So now what happens to my inches? They cancel out. And then I can have my final answer. Which is 91.44 centimeters. So notice how, as I was doing this, I started with a unit. The unit I wanted to get rid of went on the bottom. I had a new unit, but that was not the right unit, so it had to go on the bottom. This unit also was not the right unit, so it had to go on the bottom. And they cancel each other out until you finally end up with the unit you were looking for. That is the power of dimensional analysis. So let's try to solve some problems using dimensional analysis. So the first thing you want to do is write your given down. Multiply in a horizontal line. The unit of your given goes on the bottom because you want it to go away. The unit you are looking for goes on top. Now remember I said, refer back to this later on. You're going to need to know these conversion factors. So you could look it up in your book, on the internet, or maybe you just know it. But I happen to know 1 liter is 1,000 milliliters. So what am I physically putting in my calculator? 22.0 times 1 divided by 1,000. And when I do that, I get 0.0220 liters. Notice this has 3 significant figures, and so does my answer. And my milliliters canceled. Let's try the next one. 55.6 kilometers to millimeters. So the unit kilometers is to go on the bottom. I don't know how many millimeters are in a kilometer, but I do know that there are 1,000 meters in 1 kilometer. So if I stopped here, my answer would be in meters, but I don't want meters. So I need to get rid of meters. I want millimeters. And I know that there are 1,000 milliliters in 1 meter. So then when I punch all of this, and I'm going to write this in scientific notation, three sig figs. These conversions factors do not affect your significant digits because they are exact measurements. They are exact numbers, not measurements. So they do not affect significance. Okay, let's look at the next one. So here I have 2.01 centimeters cubed. Now notice this cube. That's kind of interesting, right? I don't know the relationship between cubed units, but I do know there are 100 centimeters in 1 meter. And if I cube that all, so that effectively gives me Or you could have wrote it 3 times. Which is the same thing. Or you could write this as 1 cubed is just 1. And then you can put in your calculator 100 cubed. And when you do that, you get 2.01 times 10 to the minus 6 meters cubed. Remember, when you have a cube like that, it isn't straightforward. You have to do it 3 times or cube it. Okay, our last example. I have 72.4 miles per hour. And we want to change it to miles per second. So the unit on the bottom is the one we want to get rid of. So we have to write it on the opposite position of where it is. So it's on the bottom. So I want it to go away. So I have to now write it on the top. I know how many minutes are in an hour. So in 1 hour, there are 60 minutes. So here my hours will go away and I will have miles per minute. But I don't want miles per minute. So because the mile is on the bottom, I have to write it in the opposite place. In 1 minute, there are 60 seconds. So then when you calculate that, the minutes go away. So I still have miles on top over seconds. And that would be your answer. So we're going to have some more practice worksheets on this. If you have any questions, please let me know. And that is the end of chapter 1.